So I'd like to start a series of lectures on model discovery. So the idea here is to actually measure a system and try to back out or infer what the governing equations were that produced that time series data. We're going to start off with a series of lectures. First, we're going to look at thinking about model discovery for differential equation systems. Then we'll move it to partial differential equations, so full spatial temporal systems. And then finally, we will look at alternatives when, in fact, we don't measure the full state of the system. And we start relying on what's called time delay embeddings to discover this and discover latent variable spaces. So the idea is pretty simple and kind of from a high level, we just want to think about the differential equation. And so that in general, I have some nonlinear differential equation, and I'm also going to collect data from that differential equation. It could be noisy measurements and so forth. So, but either way, I'm going to time series data for some vector y as a function of time. And the whole idea here is I don't know what f is. So what I would like to do is come up with an algorithmic way to figure out, can I do something about a discovery process where I can determine or back out the most likely f possible that would come from the data itself. So of course, we can start thinking about this and thinking about all the equations we typically write down in our classes for modeling different systems, and we always prescribe an f. So for instance, if you do some dynamics of electromagnetic waves, you might write down Maxwell's equations. Or if you're looking at quantum mechanics, you write the Schrödinger equations. So all these scenarios, I tell you what f is so that you can run a forward model, maybe with some parameter variations to discover the dynamics of that system. Okay? But here the idea is I now have maybe a bank of sensors to measure a system, and from those measurements alone, I would like to determine the f. Where this is really practically important is things like biology, where oftentimes we don't necessarily know the governing equations at some macro scale, but we have a lot of recordings. And what we'd like to do is infer some kind of governing equations of the dynamics of that system. So what we're going to do here is start with a very simple example and the architecture, and from there we're going to build forward into discovering differential equations. So the math behind this is that we're going to basically take this and simply turn it into ax equal to b. That's going to be the goal. And then we're going to solve ax equal to b. Okay? And there's certain things we want to do to regularize the solution to ax equal to b to make this work. So that's what we're going to talk about in this lecture. So first of all, what we can start to ask questions about is, what are the potential forms of f that it could have? So for instance, if this was a single degree of freedom system, y is just a state of the system. It's not, so for instance, a vector system where you have multiple components of the state or n-dimensional system, just y. You might say, well, f could be, what are the possibilities? F might be contained in something, it could be y squared, y cubed, so polynomials. Those are always good guesses. We always have a lot of models that have polynomial dependence. You could also have things like sine y, cosine y, so forth. So these are all candidates. Sorry, let's get rid of this. These are all candidate functions. I don't know which ones it could be, but this is only limited by my imagination. Right? So I'm going to propose that this is made up of some potential library of functions. Okay? So there's my library. I construct it. The main thing you're going to assume here is that for any model I measure, there's only a couple of these terms that matter. Consider the pendulum, for instance. The pendulum, y double prime equals sine y. Right? So there's one right-hand side term. And of course, we break that down to a system of 1x1s. And the idea is that the right-hand side is made of a sparse number of terms from this library. Now, this idea of sparsity is really important. And it's going to start framing what we do at ax equal to b. In other words, when I do this, what I'm going to do is I'm going to solve AX equal to B, and I'm going to regularize by promoting sparsity. And when I regularize by promoting sparsity, it's going to subselect a small number of the terms in my library to construct the dynamical system. Okay? So let's make this more formal, and let's see how we can turn dy dt into AX equal to B. So first of all, I have the library. I have time series measurements of the system. And so I'm going to start framing what I can do with this. So here's what I'm given. And let's call it T of n. And I have a bunch of time measurements. So I'm given a bunch of time measurements of the state of the system. Okay? And so what I can do with this is I can say, okay, given that, then what I'm going to do with it is I can compute dy dt right here. I need this, right? With y as a function of t, I can now approximate dy dt. So in fact, let's go ahead and do this. So you can say compute y dot. Now differentiation is an important process here. What we're going to do in the example that follows is we'll just do finite differences. But really, one of the keys to successes of this method is to use much better techniques for differentiation than finite differences. So you can use, for instance, total variational derivatives. And at the end of the lecture, or at the end of this thing, there's a set of code base that will allow you to download to do a more robust job with this. Okay? So given y dot, that means I have this here. Okay, I have the left side of the equation. So I'm going to call y dot my vector b. Okay? And once I have y, I can also now construct libraries of the dynamics. So let's make a matrix, theta, of my libraries, which contained in this are all the possible functions that I have. For if this is a single degree of freedom system, I could put y in here, y squared, y cubed, sine y, something like this. So this is a matrix, and each column of that matrix is a unique term that could be part of my right-hand side. I could have y squared, y cubed, limited by your imagination. So you can put in a lot of different things there. I could put 1,000 library elements in there if I wanted to. Okay? So those are all the ideas that I'm going to put in the library, all the potential right-hand sides I think could be making up F. Okay? Polynomials are always good choices. Part of the reason we think about polynomials, if you look at a lot of the governing equations we have in dynamical systems, they have polynomial right-hand sides. Okay? But also sines, cosines, exponentials. You can put in things that you'd like in there. Okay? This is going to be my matrix A. So each column is a distinct potential right-hand side term, and each row is a time snapshot. So row 1 is at time 0, or at time n equals 1. Row 2 is at time n equals 2. Time n equals 3, all the way down. So generally, I take a lot of measurements. Okay? So generally, this is going to be a tall, skinny matrix, because I'm going to take maybe 10,000 measurements in time, and maybe I have 100 library elements. Okay? So this would be 100 by 10,000. Okay? Tall, skinny matrix. The only thing left then is I have A, I have B, is I want to say that my right-hand side, then, y dot is equal to theta times some vector c. So I compute y dot. Here it is. So it's a vector b, right? So that's my vector b. This matrix here, A, and then this would be the x. So AX equal to b. And what c is here, c is the weight of each single one of these terms. It's unknown. I have this, So one easy thing to do is just simply say, oh, well, C is easy to determine. It's just the library backslash y dot. AX equal to B, and I could do a pseudo inverse. Okay? Now, remember, this is a very large overdetermined system because it's a tall, skinny matrix. The other thing I could do here is I know one thing about C. Out of all these libraries, only a few should matter. So I may want to solve this AX of B problem by promoting sparsity and using lasso, for instance. I could do a sparse regression with L1 and just solve AX equal B with lasso. This is the entire structure. It's actually pretty simple, right? You just say, I have a dynamical system measuring. I put in some potential library of candidate functions. And so if you give me the time series measurements, I can compute their time derivatives. I can compute a library of potential functions, AX equal to B. It's that simple. Okay? A couple keys to this. There will be some references at the end of the lecture or at the end of the on the website that will direct you to some more sophisticated things you do with differentiation. But you do need good differentials, good differentiation schemes. So again, something like total variable derivative is a good way to go. And you need a sufficiently robust set of library elements. And also, hopefully, lots of measurements in time. But if you have that, you can do a regression and get this to work. Okay? Or I'll show you how it works. So that's the basic mathematical architecture. Model discovery using AX equal to B. And it really is that simple. And I'm going to show you an example here on the van der Pol equation. And you'll see how this thing all works out and how we would construct this in practice. Okay. So a particular example we want to consider to just execute this is we need one good example. So I'm going to give you the van der Pol oscillator, which is a nonlinear oscillator. And in particular, I'm just going to give you the time series measurements of the state of the system. And your job then is to back out what was the differential equation that created those times, responsible for creating those time series measurements. Okay, let me finish erasing here. Then we can go to MATLAB. So, erasing is a bit challenging on this board. All right. So the van der Pol oscillator. Let me write it down for you. So what it is, it's an oscillator with a non-linear damping. There it is. So that's the van der Pol equation. And really quickly, I'm going to explain it to you. The damping depends upon the amplitude. So if the amplitude is above 1, then this is positive. This acts like a damping. If it's below 1, then this is negative, and it acts like a gain. So what you find in this situation is if your amplitude's large, it decreases to a limit cycle. If it's low, it increases to a limit cycle. And it comes on to some stable limit cycle behavior. And I'll show you this. And in fact, as you crank up mu, it becomes highly nonlinear. And as mu is small, it looks like a perturbation of a regular linear oscillator. Now, we can always rewrite this as a two-variable set, which is if you say x1 is equal to y, x2 is equal to y prime, then what you have is x1 prime is equal to x2, x2 prime, okay, is equal to mu 1 minus x1 squared, x2 minus x1. Okay? So that's our system. So we're going to measure x1 and x2 in time, and we're going to see if we can recover this set of equations here. Okay? So that's the goal. It's a simple problem. We'll run a simulation of it for you to look at what this thing looks like. And then once we have that, we're going to think about now, if I just gave you the data, would you be able to recover this? Okay? That's our first intro to this kind of model discovery platform. Okay? So that's going to be the goal. Let me see. Maybe I'll leave that up there. And I will bring up MATLAB. Okay, so we're going to start off with some code. Oh, that's going to cover it up, so let me just erase. And in this code, what we're going to do is first build our data set. So of course, this is going to be synthetic data, but really what we're just trying to show in this lecture is a proof of concept. Can this thing actually work? Then we'll noise up our data, see how well it works, and see how it breaks down. Okay? As with anything, if you add enough noise, nothing will ever work. So that's just a general principle in life, right? You just keep adding noise, things break. And that's no different here, but there's a range in which you can tolerate some noise and it will still work quite nicely for you. So first of all, let me show you the right-hand side. Here it is. Oops. There it is. Okay, this is the right-hand side function for the Lorentz equation. I'm going to show it to you now, and then we'll just work on the equation. So the right-hand side is x1 dot was equal to x2, x2 dot was equal to mu 1 minus x1 squared times x2 minus x1. So it's exactly what we just broke down there. So that is the right-hand side for my OD45 solver. So now you've taken a look at it, you can see, okay, there's van der Pol, parameterized by mu, which I send in here. Okay? And so now let's go ahead and build a code that's going to call on that. All right. So first what we're going to do is we're going to define some time points. So we're going to say dt is going to be 0.1. And time is going to go from 0 steps of dt to 50. So what I'm going to do is tell it what kind of snapshots I want. So if time is 0.01, what I'm going to get out is a time series with 5,000 points. Okay? And those 5,000 points is what I'm going to use as a time series measurements to try to see if I can back out that van der Pol oscillator. My initial condition, let's make something up, 0.15. And mu, which is the parameter telling you how nonlinear it is effectively, let's make it 1.2. So I have a time, I have an initial condition, I have this parameterization of the equations. Now let's go solve it. So I'm going to run OD45 to generate the data. And so I'm just going to give you the time series and see if you can recover things. Okay, so Ty is equal to OD45. We're going to call right-hand side dynamics. Send in our time, send in our initial data. Then here would be setting in our parameters for how accurate we want the OD45 to be, but we're just going to leave the default, and then mu. So that's an OD solver. You're going to go call this, call the right-hand side, step it forward in time, give you back the data at every 0.01, all the way to time 50. So that's what we have. And let me just show you what this looks like. Plot Ty, first component, second component, line width 2. Oop. Ah, gosh. Okay. Okay, so let's run this. So when we run this, oh, I think I have a missing something. Let's check what MATLAB's complaining about. Oh, not that one. Sorry here. Okay, what did it say? Oh, hold on a second here. Let me just double check my right-hand side. Actually, I might be in the wrong directory. Oh, I'm in the wrong directory. Okay, so let's make a new right-hand side function. So, new. So this is going to be the right-hand side function. It was in a different directory. Function, right-hand side, is equal to right-hand side, dyn, tx dummy, mu. That's what I sent in. And my right-hand side is equal to x2 mu times mu times 1 minus x1 squared times x2 minus x1, and then close that off, and there we go. Save. Save. Okay, now I should be able to go back here and run this. Okay, so now we're running this code, and we run it out from time 0 to 50, and here you go. So this model is something we're going to use quite often throughout these examples because it's sufficiently simple, yet it kind of gives you something interesting in terms of the dynamics. So here's the Vanderbilt oscillator. So you can see that it has sort of this exotic time profile, right? But it's clearly periodic, so it's a nonlinear oscillator. And so here's the challenge. If you did not know this came from Vanderpool, and I just gave you this time series data, would you be able to recover the Vanderpool? Okay, so this is a model discovery through the regression. Now I've made the comment, this is just AX equal to B, and that's exactly what it's going to be when we do the discovery. So that is our data. That's what we're given. Can we back out the actual model? So let's go ahead and try to do this. All right, I'm going to kill that window, and here we go. So put some of these down here. All right. So what we want to do now is we have these two variables. x1 is equal to the first column of this thing. We have x2 is the second column of y. And I label them particular just so we have x1 and x2 in our mind. Remember, we're trying to discover x1 dot equals and x2 dot equals. That's the frame what we have. It's a 2 degree of freedom system. And we're trying to discover the time with the time series measures of each what the equation was. Now, by the way, I'll make a comment that in the third lecture of this series, we will address the issue of what if I only have x1 and there was an x2 but I don't have measurements of it. In other words, it's a latent variable. What would I do then? And we'll talk about how to handle that then. And again, this is all on the AMath 563 website. So if you want to get there, there's a link on the YouTube video towards that website which has all that information. Okay, so there you go, x1, x2. Let's go discover some equations. So that's what I start with, data points. And now what I need with this data is I need time derivatives, right? So that was part of the issue is like it's y dot equals some library times c. So I need to compute the derivatives of both these time series data. So a simple way to do this is say, well, what's the length of these vectors? It was the same length as t. And for j equals 2 to n minus 1, what I'm going to do is use a center difference formula. I'm just going to do rise over run. Simplest thing you can think of for computing a derivative, right, which is just slope, rise over run. I'm going to do that. And what I'm going to do is for all the data in that time series except for the first and the last point. So I'm going to use a center difference formula, which says it's the point in front minus point behind over 2 delta t. Rise over run. That's going to be my very simple and rough approximation for a derivative. Okay? But my time steps are 0.01, so I have a very fine resolve. I have no noise, so that helps a lot. Later we'll add noise up here and see what happens. Okay? So what I'm going to do is compute these derivatives. So x1 dot is equal to, well, what you do, in fact, this is the j minus first point. Notice I'm starting at 2, so I'm starting at the second point, so that's why I subtract 1 here. So the first point of this, subtract 1, is at 1, and then 2 all the way up. So I differentiate all the interior points. And what this is point in front, x1, j plus 1, minus point behind, xj minus 1, right? Divided by 2 times dt. x2 dot is j minus 1 equals x2 j plus 1 minus xj minus 1 over 2 times dt. There you go. First derivative for each. So now what I have is the time series data. Okay? So I'm ready. I have that. So that's my, in AX equal to B, I just computed B. Now I have to compute the matrix A. The matrix A is my library of potential right-hand side functions. Okay? So let's go make some. All right. So what I want to do is, remember, I'm now throwing away the first and last point, right? Because I did that with differentiation. So I want to make two new variables, x1s, which is x1, the second to the n minus 1 point, and x2s, which is the second to n minus 1. So I throw away the endpoints because I don't have derivatives there. I mean, I could easily get them, but it's not worth the time to write it. Just take this internal states of the system. There are my time series, and let's not make a library now. And the library of possible functions, a is equal to. Well, what could it be? Well, how about it depends upon x1? What if it depends on x2? What happens if it depends on x1 squared? Or x1s times x2? Or x2 squared? Okay? Or what about the cube? In fact, I'm going to go and do all polynomials to degree 3. So x2s squared times x1s, and then x1s squared times x2s, and then x2s cubed. So in fact, let me just do a continue here with a dot, 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 so you can see it all. Like I said, I didn't do a very good job cutting that off. How about here? I'll do a dot, dot, dot there. Okay, that should get all the terms. So almost all the terms are there. Okay? Let me make it just slightly bigger. Okay, so here's my library. And in my library, I have polynomials up to degree 3. I have, it depends on x1 or x2, depends on x1 squared, or x1 times x2, or x2 squared, or x1 cubed, x2 squared, x1 squared, x2, or x2 cubed. So again, this is just illustrative for us, right? I just said, what about all these polynomials up to degree 3? And what you can see here is I have quite a number of terms, like something like 9 terms, right? So I have 9 possible terms. You can even put a constant in, 1, right? So those are possible libraries. So I have 10 terms. And what I believe is that only a few matter. So the idea is to do a regression now, and we can just, and by the way, remember 5,000 points. So this matrix has 5,000 this way by 10 this way. Okay? It is a very tall, skinny matrix. And I can easily solve it with the pseudo-inverse or the backslash. So let's just do the backslash. So x1, my discovery of x1 is equal to a backslash x1 dot. And my discovery x2 is equal to a backslash x2 dot. Oh, and by the way, I have to lay the x1 and x2 to make them column vectors. So I just did that there. There you go. I solved it. I told you it was as simple as x equals to b. There's the backslash. So x equals to b, as I promised. Okay? Now what we're going to do with this, x1 and x2, is we're actually going to look at what happened with the solutions to this. So, right? So we're going to do a plot here. Bar x1i, xi1, and subplot 2, 1, 2, bar xi2. Okay? So what I'm going to do here, I'm going to go through this, build my library, solve the equations, take the derivative, build a library, backslash. Simple as that. All I'm doing is x equal to b. And the question is, what comes out of this? What comes out of this, the bar will tell me which ones are non-zero. We're going to look at what we get. Okay? So let's run this thing. So there we go. Oh, something crashed. Let's just double check. All right. Okay. Oh, there we go. I made a mistake here. There. That's an x1, and that's an x2. Okay. Run again. Hopefully got it. No, still. Sorry, apologies for the errors, but you're seeing live coding. Okay. Oh yeah, so I have to differentiate this, and I think right now, so let's see here. So x1 dot, okay, I have to take these, and I have to make them Oh, they're already column vectors, right? I think, hold on one second here. So x1 dot, is that a column vector already? No, it's a row, so I have to lay it on its side, row. But x1, okay, so x1 and x2. I think up here, I have to do, no, those are column vectors. Let's see, what's it complaining about? Hold on. Oh, the 1. Okay, all right. For the moment, this is not the right size, so I'm just going to take out the constant. You could put a constant in, but you have to put it in as a set of 1s. Okay, apologies. Now let's run it. x2 dat. Oop. Dot. There. Gosh. Okay, lots of mistakes. Here we go. And there we go. All right. So here is the result. And this is the fairly remarkable thing. In fact, let me make about this size, and I'll come here. What I'm going to do is scroll this up so that we can see what the A was here while we look at the picture here. Okay, there we go. So here is the result. I did the backslash. What did it say what x1 dot should be? x1 dot is equal to, here's the value of the coefficients. And they look to be all 0 except for this one. And what is this one? Well, it's the second one in, which is x2. So x1 dot is equal to x2. It got that one right? It clearly says x1 dot is equal to x2. Then we can say, well, okay, let's, what about the next one? Let's, what does the next equation say? It says x2 dot is equal to, this is x1, x2, and then this term over here, right, is, it's the 8th term, and the 8th term is x1 squared x2, okay? And if you remember, that's exactly the Lorentz oscillator. The Lorentz oscillator, let me write it down, just so we have it, was x1 dot is x2, x2 prime is equal to mu 1 minus x1 squared x2 minus x1. Okay, so that's what we had. That was our exact system. So the first one gets this. The second one, let me just fold this up a little bit so it's out of the way. So the second term, you have a mu, you have an x1 squared x2, that's exactly that term here. You have a minus, you have a mu x2, which is this one here, and then you have a minus x1, which is this one there. Got it. Just with a backslash. And by the way, the backslash, when you have large overdetermined systems, automatically promotes sparsity through its QR algorithm that does this. So we recovered this. Not only do we recover it, let's take a little bit closer look at this thing. In fact, we recovered it, but there's a little bit of something here that you should see. In particular, let's zoom in. If I zoom in here, okay, these are not 0. Let me zoom in a little bit more. See it there? They're tiny, but they're not 0. Okay? So oftentimes what you can do with something like this is just threshold them out. You say if you're below a certain level, you throw it away. So one of the ways to do something like this is to do least square fitting or backslash and throw away small terms. You do it with the backslash, is easy. And then you can say, oh, I'm going to threshold those out because what dominates is this here, and this is, in fact, if you see here, that's 1. It's at a value of 1, which is exactly what it should be. Okay? Now the other terms, same thing. Let's go zoom in. If I zoom in down here, you'll see none of these are actually 0. They're just mostly 0. Oops. There we go. See, if I zoom in further, there, see? None are actually 0. But you have 3 dominant terms which are exactly corresponding to these terms here. Okay? So in fact, let's look at the coefficients we got. So for this one here, if I look at what this is, if you look over there, it says 1.2. It's right about 1.2, which is exactly what I picked mu to be. So it's mu x2, which is 1.2. So it nails that term. Here, it's at -1. You can see this, -1. That's exactly what the value should be. And for the other term, here it is. And again, same thing. It's at -1.2, which is exactly what it should be here. So it's actually quite remarkable. All we did was took the time series data, built a library of potential terms, which is A, took the derivative, which is B. We said AX equal to B \. You can also, if you want to promote more sparsity, you can just do lasso directly on this. And that will also zero out most of the terms. In fact, in that case, you can actually make it so that all those terms, instead of being really small, are exactly 0. Okay? So that's model discovery for you. I just discovered an ODE by doing time series measurements and setting this up as a framework of AX equal to B to do this. Now let's see what happens when we add noise. And I'll just do this. So what we'll do here is if you look at x1, right, the x1 variable, let's go ahead and, so x1 itself, right, is a 5001 by 1. So what I'm going to do is I'm going to add noise to it. Okay, so here it is. Oop. I'm going to say that my noise level, and we're going to play around with the noise level and see how this impacts things. So let's make it 1 for now, and plus rand n. Actually, I'm going to put noise in front of it. Noise times rand n, and this is a 5001 by 1, right? Same thing with x2. Add noise to that, plus noise times rand n, 5001 by 1. I don't know how big this noise is. Let's just run it and see what happens. When you run this, right? Okay, so first of all, you see what happened here. Looks kind of bad. Okay. In fact, I should make this figure 2 so we can see what the time series data looks like itself. So this will be figure 2. So we can look at how much noise we actually put on this system from running the simulation. Well, actually, I plot it before I put noise on, right? So what I really should plot here is, let's make figure figure 3, and we will plot t versus x1, t versus x1, t versus x2, line width 2. Okay, let's run that. Okay, so figure 3, that's a lot of noise. Way too much. So let's bring the noise down, and you can see if you have a lot of noise, pretty tough to pick it out. In fact, here you can still see that the x1 and x2 give you good signatures, but here, look at that, x1 really comes on. You can still get a good signature here, but everybody's being lifted up. So when you have a lot of noise, it's really hard to sparsify and select. Okay, that's just a thing. But let's go ahead and take less noise in this. Let's bring the noise down to 0.2. Here you go. So even with 0.2, here's the data. So it looks noisy, you know, but you can still see at least roughly the oscillation pattern. And here are your results. So if you're going to threshold and say which terms dominate, if you say which terms dominate, you could see clearly you got the right term here, and you got those 3 terms there, but everybody else is slowly coming up. Okay? So noise will have an impact, but you can still see you don't do too poorly. Okay? You can actually still threshold, but your threshold's going to get a little bit bigger, right? Because everybody's getting lifted off by the noise. So ultimately what I've showed you is a principled technique, right, for discovering models, right? So you say, I have x dot equals some unknown f. If you give me the time series data, My job is simply to construct AX equal to B and solve it from there. That's how, in some sense, how simple it is. And again, if you have pretty clean data, you have a good way to differentiate, you can get pretty good models. Okay? If you have enough noise, a lot of noise, or if you have to have latent variables, there's some other techniques to handle this. The next lecture is going to handle how to discover PDEs. It's going to be a very similar structure, just a much bigger AX equal to B problem.